Welcome. We started with some illustrations on the microscopic balances. Today we shall be taking some more of such illustrations, and in this we shall be looking into the various transfer equations, momentum, energy, mass, etc. So first let us go with the continuity equation. As you know that continuity equation gives us the overall mass balance for a system, and continuity is overall mass balance, whereas separately we will do the mass balance for the species. So here we assume that we have a steady state incompressible two-dimensional flow of a Newtonian fluid with constant viscosity. Now all these phrases should be noted very carefully, because depending on what we assume, our balance equations will change. So because of the steady state assumption, we will not be having any time differential in the equations. Then because of incompressibility, we shall be having the density to be constant. So we can take out the density from any of the differentials. Then we have two-dimensional, that means in space when we have x, y, z or r theta z or r theta phi, then we can drop one of the dimensions. A Newtonian fluid means the stress in a fluid can be given in terms of the Newton's law of viscosity, that is stress equal to mu into dou v by dou y. So with all these assumptions, let us see how the continuity equation looks like. So here we are assuming that the velocity has three components u, v, w, and we are taking the w to be 0 and two-dimensional. So we are neglecting all the z differential, that means we are taking w to be 0 and we are taking all the dou by dou z term to be 0. Okay. So with these assumptions, we are writing the continuity equation like this, and also because it is incompressible, so rho is also constant. So because rho is constant, so we are able to take out the rho from the differential. So otherwise these expressions look like dou u by dou x plus dou rho v by dou y. So they look like this, and because of incompressibility, constant density, we are able to take this rho out of the differential, and because of steady state, we are saying that dou by dou t is equal to 0. Okay. So with this understanding, we are able to get this particular equation. Now our intention is to get a non-dimensional form of this particular equation. Now for non-dimensionality, first let us see what are the variables involved here. We have x, y, u and v. So for each of them, let us see that how we do it. Now let us suppose that for the x direction, we have some characteristic length. So first we have to define some characteristic value with respect to each of the variables. So for x direction, we are saying that let L be the characteristic dimension. Now L can be anything. L should not be interpreted as kind of length. It can be breadth, it can be width, anything. Okay. So let us assume that this L is that kind of length in the x direction. So we are having this x star as the non-dimensional x. So this x star is defined as x by L. Now in this case, as I mentioned you earlier, that sometimes by doing the non-dimensionalization, we also land up with some normalization. Now if the x varies between 0 and L, we find that the x star will also vary between 0 and 1. So that way x star is not only non-dimensional, but it is also a normalized non-dimensional number. Okay. So if x varies between 0 and L, then means x star will vary between 0 and 1. Okay. So this is normalized. So in this fashion, we can also define another y star, that is non-dimensional y, in terms of the same length. Now please understand that this characteristic length need not be the same in the x and the y direction. So, I can also say like x star, I can put something like this, that x by Lx, and y star I can put something like y by Ly. That means this Lx is the characteristic length in the x direction, Ly is the characteristic length in the y direction. Okay. So, in this fashion you should be understanding, or you should be making this kind of non-dimensional numbers. Okay. So, for simplicity's sake, here we are taking these two L's, that means in this case we are taking Lx equal to Ly equal to L. Okay. So, this is the understanding. Now, next coming to the velocity. Here again we can define some kind of characteristic velocity. Now, in this case you see that u and v, we have these two velocities, and generally what happens that whenever a fluid is flowing, we take that away from some surface, we take that it is going with a free stream velocity. So, we say that v infinity is the free stream velocity. Okay. Well, when this is free stream velocity, we can take it to be same in any direction. So, that is why you see that when we are non-dimensionalizing u and v, we are taking the same characteristic velocity. Okay. So, with this understanding, we find that these are the four ways we are able to do the non-dimensionalization. Only one more thing to be noted is this, that u star and v star, they may be or may not be normalized. Okay. Generally, you will find that whether you will be restricted to v infinity or v will be restricted to v infinity or not, that will depend on the physics of the problem. Okay. So, with that understanding, we say that they may be or may not be normalized. Now, let us go ahead. Here we have this non-dimensional form of the continuity. What we have done with those u and v, we have substituted in terms of u star and v star, and x and y we have substituted in terms of x star and y star. So, now you can see that you can take out the v infinity L from the differential, and we get this particular equation. And you see this non-dimensional equation in this case has the same form as the dimensional form. Only thing it is seen that it is replaced by the non-dimensional velocity and non-dimensional length parameters. Okay. So, this is very straightforward way of finding the non-dimensional form for the continuity equation. Next, we come to the momentum equation. Now, again in the momentum equation, we are assuming that it is steady state, two dimensional, and a flow of a Newtonian fluid with constant viscosity. Now, please understand, when we say constant viscosity, it means we are neglecting any kind of variation of the viscosity with respect to temperature and pressure. Now, if it is with respect to temperature there is some variation, then understand this, that we have to consider also the energy balance. Okay. So, for the time being, to avoid the use of the energy balance, we are not going to take the viscosity to be a function of temperature. For pressure, generally we do not have any explicit equation when we talk of this Navier-Stokes equation. Generally, pressure is taken indirectly through the continuity equation, about which I shall not be talking in other courses, like in CFD. It is taught that how we can take the pressure variation into account. Now, let us look at, with these assumptions, let us look at this particular situation. This is the equation for the x direction momentum equation, and this is for the y direction momentum equation. Now, if you look at the full momentum equation for the Newtonian fluid, you will find with this is added W dou u by dou z. So, this term is added here, and when you go for this term, you will find it is coming like dou 2 u by dou z square. Okay. Now, please understand, in this x direction equation, we do not have the body force here. Now, body force, as I said, that body force can be many things. Okay. Generally, the most often body force is a gravity, and gravity is generally vertical. Okay. So, that is why you find that in the x direction we are not having any gravity effect. On the other hand, in the y direction we have the gravity effect. Okay? But please understand, it is just not gravity, it may be some other body forces which may be there in the source term. Now, because it is steady state, so we are having dou u by dou t equal to 0 for this, and dou v by dou t equal to 0 for this. Okay? So, that is how we are finding that we are able to negate this term. So, similarly here also we will be having a w dou v by dou z, and here also we shall be having a term dou 2 v by dou z square. So, because of our assumption of independence with respect to z direction, so these two terms goes to 0, okay, and because we are assuming that it is two dimensional velocity, it is w is 0. Okay. So, that is how we are reducing this whole 3D equation into this 2D and with the steady state assumption. So, similar to the one what we have done for the continuity equation, we are also defining all these equations, all these non-dimensional equations like this, that x star equal to x by L, y star equal to y by L, u star equal to u by v infinity, v star equal to v by v infinity, and here comes the thing next is the pressure. Now, in this case the pressure has to be somehow obtained, a non-dimensionalization of that have to be done through some other kind of combination of the existing parameters. So, you can see that if you look at the Bernoulli, then you can see that pressure is taken, the pressure head we have like this, P by rho g plus V square by 2 g plus Z equal to constant. So, you can see that we can correlate the pressure with the velocity. Okay? So, you can see that that kind of inferences are taken to find this kind of characteristic pressure, we call it characteristic pressure, okay? And so get this particular non-dimensional pressure. Now, what we understand by this characteristic pressure, let us try to understand this a bit more. Many times you find that a flow comes and suddenly it kind of gets stopped by some kind of hindrance. Okay, for example, if you want to find out the point by point velocity using pitot tube, then you find that in pitot tube, which is taught in the fluid mechanics, you find that we take the what we call stagnation pressure. Okay, and in that it is assumed that when a fluid is brought to rest suddenly, the whole pressure energy gets converted to its kinetic energy. Okay? So, that you can assume that this particular non-dimensional pressure is something like the stagnation pressure, in which a flowing fluid is brought to rest. Okay? So, that way we take this non-dimensional form of the pressure. So, after getting these non-dimensional numbers, we plug in all those non-dimensional parameters in the momentum balance equations in the x direction, y direction, and we get this particular equations. Now, after again you can take out all the constant values from the differential and you will get this equation, and again you can see that these whatever you see in the parenthesis, they look similar to the one which is there in the our original dimensional form of the equation. Only thing you see that some kind of terms get included with the convective terms. This is the convective term, inertial terms, the pressure term, and this particular term for the viscosity term. Okay. Now, understand this particular term here is still dimensional, it is not non-dimensional, because each of these terms are dimensional forms. Okay. So, we rearrange the equations by dividing by rho v square by v infinity square by L, and we get this particular equation for this and this. Now, you can see here that we get some non-dimensional numbers, and this particular thing is the what we call inverse of the Reynolds number. Okay. And This particular thing is the inverse of the Froude number. Now, what is Reynolds number? We know that Reynolds number denotes the relative importance of the inertial force to the viscous force. Now, what is the meaning of this? Now, suppose a fluid is flowing over a surface. Okay? So, because of the viscosity of the fluid, there will be a drag offered by the surface which will try to retard the motion of the fluid. Okay? So, that is what we call the viscous force, which is generated due to the viscosity of the fluid. And you know that there are something called the ideal fluid. An ideal fluid, we say that the viscosity effect is 0. That means ideal fluid are non-viscous. Okay? In that case, there will not be any kind of viscous force. Okay? And in that case, you can easily see that Reynolds number will tend to infinity. Okay? On the other hand, even if it is not an ideal fluid, okay, in that case what we say that the inertial force means which is coming due to the motion of the fluid. Now, as the motion of the fluid is increasing, it will be kind of over dominating the viscous drag, and due to this what will happen that the fluid nature of the flow will change. And in this manner you perhaps also know that when the viscosity is very high compared to the inertial force or the velocity, then we get what we call the laminar flow. Okay? And when the viscous effect is negligible in comparison to the inertial force, then we get the turbulent flow. Okay? And this Reynolds number is the deciding factor. We look at the Reynolds number value to decide that whether we are having the turbulent flow or the laminar flow. And perhaps you also know that there will be something called the critical Reynolds number for a given situation. For example, in a circular pipe, the critical Reynolds number is taken to be about 2100. What it means is this, that any Reynolds number below this 2100 will represent laminar flow. That means, even if we disturb the flow, if the Reynolds number is less than 2100, the flow will again go back to the laminar region. On the other hand, above 2100, there will be a transition zone, okay, that there will be both laminar and turbulent coexisting. But generally, for our simplicity's sake, what we do that above this 2100, we take that flow to be turbulent, and in that case what it means that even if there is some kind of disturbances there in the flow, it will never come back to laminar, it will stay turbulent. Okay? And you know that turbulent flow, when you want to kind of maintain a turbulent flow, you need to supply energy from outside to keep the turbulence, because turbulence always try to dissipate the energy. Okay? And if dissipates the energy, it has a tendency to come back to laminar region. But when this Reynolds number is quite high, then it will not come back to laminar region, it will stay in the turbulent region. Similarly, we have this another number we call the Froude number, and this Froude number is the ratio of the inertial force to the gravity force. Now, gravity force, when it happens that, for example, when you have the waves on a river or in some kind of channel, these waves are formed due to this gravity effect. You can see that waves come and then they can fall. Okay? So, this is due to this buoyancy and then gravity. So, this buoyancy effect or gravity effect, they are also coming into picture in dictating the motion of the fluid other than the inertial force. Because when you look at the ocean or some river, at the surface of the ocean, okay, or near the surface of the river, you do not find any solid surface. Okay? But you still find that the fluid motion is restricted, it is not just going away, it is just because due to this gravity effect. Okay? So, whenever we have this gravity effect, then we talk of the Froude number and gravity versus the inertial force, inertia, that is the motion of the fluid. Okay? So, you will find that when we non-dimensionalize the momentum balance equation, it will be not continuity, it will be momentum equation. Okay? There is a mistake here. This is the momentum equation. So this is the way we can visualize the momentum balance equation. You will find that I have taken some very simple examples of this, but you will find that in reality there could be many other situations, and as we have discussed in my earlier lecture, I took the example of a flow over an inclined surface or a flow between two concentric cylinders. In all these cases, you will also find that you can carry out such kind of analysis now in terms of all these non-dimensional numbers. And you will find that when you non-dimensionalize any of these equations, whether continuity equation, whether momentum equation, you will find that generally you will always land up with some or the other non-dimensional numbers, and these non-dimensional numbers will account for the various effects in a given system. So, here we are finding that we have Reynolds number and Froude number, but this is not restrictive. For other situations, we have many other type of non-dimensional numbers, and about which we shall be looking in the other lecture. Now we come to the energy balance equation. In the energy balance equation, so again we are taking the same two dimensional steady state flow of energy equations, and here we again find that, understand this, because energy is given in terms of the temperature, which is a scalar. So, we shall be having only one equation, unlike the case of the momentum equation. So, continuity and energy will be only one equation each, but momentum will be three equations, okay, because velocity has three components. So, here again you see, because of steady state, we are having this dou t by dou t term as 0, okay, and here we shall be also having something like this. So, because of this is 0, so this is not there, and similarly here we shall be also having, okay. So, this dou by dou z is taken to be 0, okay. So, that is why it is also 0. Only thing is this, here we are assuming that there is no source term, that is as if it is a non-reacting system, okay. And also you please see that we are taking the thermal conductivity to be constant. If it is not constant, it is, that means other than assuming the viscosity to be constant, we are here assuming that K is constant, okay. Thermal conductivity is constant. If it is not constant, then it will look like this. Okay. So, it is not that difficult for you to account for a variable thermal conductivity. Okay. Similarly, we are also assuming this specific heat to be constant. Okay. So, it is outside this. If it is not constant, it is simply that you have to take this thing inside this, okay, in a differential. Okay. So, here we are assuming the Cp is constant. Okay. So, with these assumptions, we are able to write this energy balance equation. Now, you see that here we have, similar to the one we have done previously, we have defined all the x, y, u, v. New thing in this case is the temperature. Now, in this case of when you want to non-dimensional temperature, there can be many ways. In fact, you can also define temperature in terms of some characteristic temperature, okay, some characteristic temperature. Now, generally it so happens that if we have, suppose a reference temperature, say T0, and say a wall temperature, that means as if the fluid is flowing over a surface and the surface has some kind of temperature, and T naught can be taken to be some characteristics, say maybe the free stream temperature. Okay. So, in that case we can define like this, but understand one thing, this temperature need not be always normalized. To normalize it, we have to make sure that temperature lies between T naught and Tw. Only if we find, suppose we are having two surfaces, at one say hot surface, one is cold surface, and we have say that one surface at Th and the rest Tc. Okay. Th means hot temperature and cold Tc means cold surface temperature. In that case, we know that if there is no other external sources of energy, the temperature must lie between Th and Tc. And in that case, if you apply this particular type of non-dimensionalization, that means you define T star is equal to T minus Tc divided by Th minus Tc. So, we know that T will be varying between Tc and Th, so that T star will be varying between 0 and 1, it is normalized. Okay? Otherwise, if we cannot ascertain that the temperature will be bounded by some values, then even if we are defining like this as is shown, it does not ensure that we are going to obtain any normalized non-dimensional temperature. Okay? So, this should be clearly understood. Now, after doing this kind of definitions, then we just simply put all those non-dimensional numbers in the energy equation, and we find we are getting this particular equation. Okay? So, these are simple mathematics, so you can do it yourself. So, we find that we are getting this kind of equations, and now we obtain this equation. Again you see the basic form of the equation remains the same in non-dimensional form as in case of the dimensional form. Only thing is this, we are getting some other terms in with all these terms, because these are the extra terms which are coming up. Okay? And now if you look at these terms, again we see that we can break up this term into two. Okay? One, this particular k by mu Cp is nothing but the inverse of the Prandtl number, and this mu by rho V infinity L is the inverse of the Reynolds number. So, we are having these two numbers. Generally, many a times we write in terms of Peclet number. So, this many a times this particular product, it appears so often. Okay? So, sometimes this is called the Peclet number. Okay? So, this PR is the Prandtl number, then R is the Reynolds number, and PE is the Peclet number. Okay? So, you find that these kind of numbers appear, as I was telling you, whenever we are non-dimensional things, and we will learn about these non-dimensional numbers in our next lectures in a very brief manner. Okay? So, these are some of the references you can refer to get some more explanations on the theories today you have learnt. Thank you.